Hello everyone, welcome back to my video lecture series on Introduction to the Finite Element Method in 1D. In today's lecture, I'll walk you through a Python code that solves the Poisson's equation in 1D using linear finite elements using the concepts that we just learned in our previous video lectures. So let's now walk through the code. So this is a Jupyter Python notebook code. These lines over here describe the problem that we are trying to solve. This is the Poisson's equation in 1D for the domain X belonging to 0 to L. At X equal to 0, we have a Neumann boundary condition, whereas at X equal to L, we have a Dirichlet boundary condition. We begin by importing some necessary Python libraries such as NumPy and matplotlib.pyplot. We then define our problem parameters. So L is the domain length, H is the constant for the Neumann boundary condition, whereas G is the constant for the Dirichlet boundary condition. We then define our forcing function f of x, which is this function over here. So right now it's defined as minus 12x squared plus 30x, but in general, it could be any function. So I would recommend you to play around with this code and try different values for f of x and see what you get. We then define our mesh. So here any is the number of elements in the mesh. Nn is the number of nodes in the mesh. So if you recall, for linear elements in 1D, the number of nodes is simply equal to the number of elements plus 1. He is the width of the element, which is defined as L over NE. And X are our mesh nodes. So we know that our mesh nodes range from 0 all the way up to L, and we have a total of Nn nodes. This cell block over here assembles the global stiffness matrix and the global force vector. The global stiffness matrix is denoted by K, and the global force vector is denoted by capital F. We begin by initializing both these entities. So K is zeros of Nn by Nn matrix, whereas F is an Nn by 1 vector. Here, Nn is the number of nodes in the mesh. In order to assemble the global stiffness matrix, we loop through all the elements and then add on the contribution of each element to the global stiffness matrix to then assemble the overall matrix. And similarly, the same thing for the force vector. So here we are looping through all the elements E. We begin by assembling KE, which is our 2 by 2 element stiffness matrix for element E, which has nodes XE and XE plus 1. So if we look back at our notes from last video lecture, so if you remember, the element stiffness matrix KE was defined as 1 over HE multiplied by a matrix 1 minus 1 minus 1, 1. So that's exactly what we have defined over here. KE is 1 over HE multiplied by a matrix given by 1 minus 1 minus 1, 1. We then define FE, which is our 2 by 1 element force vector. So let's go and look at what the definition of FE was. So the element force vector has two parts. The second part is the boundary term, and the first part is this term over here, which is HE by 6 multiplied by a matrix 2, 1, 1, 2, and a vector F1, F2. So if we multiply both of these together, then the top entry will be 2 into F1 plus F2, and the bottom entry will be F1 plus 2 into F2. And that's exactly what we have defined over here. One thing that I would note is that Python is based on zero indexing. So if you consider any array in Python, the first index is in 0, the second index is 1, and so on. So to be consistent with that, while in our nodes, the first two nodes of an element in local description are node 1 and node 2. So the forces there are F1 and F2. But to be consistent with zero indexing, I'm now calling them F0 and F1. So F0 is the force, is the value of f of x, which is where f of x is the forcing function at element xe, which is like at node xe, which is the first node for that particular element, whereas f1 is the value of f of x at node xe plus 1, which is the second node for that particular element. And then fe is given by he over 6 multiplied by an array given by 2f0 plus f1, and the second entry is f0 plus 2 f1. Additionally, we also have some boundary terms in FE. So the boundary terms are described over here. So for the first element, the boundary term is delta A1 times H. Now, based on zero indexing, The first element is actually 0. So we have a condition if E is equal to 0, then the first entry of E, so FE of 0 is equal to FE of 0 plus H, which is exactly what we have over here. On the other hand, for the last entry, we have this term based on the Dirichlet boundary condition. So we take FE and we subtract KA2 times G. So the same thing based on zero indexing is FE is equal to FE minus KE arrow comma 1, which is basically the second column of the 2 by 2 element stiffness matrix KE multiplied by G, which is exactly what we had over here. Now that we have assembled both KE and FE, we then assemble them into the global stiffness matrix and the global force vector using our assembly process. So if we go back to our notes where we defined the assembly process, so if you recall, the element stiffness matrix KE enters into the global stiffness matrix in rows E and E plus 1 and columns E and E plus 1. That's exactly what this line does over here. KE goes into rows E and E plus 1 and columns E and E plus 1. And similarly, FE enters into rows E and E plus 1 for the global force vector, capital F. So far, our stiffness matrix K and force vector F are of dimensions Nn, where Nn are the number of nodes. But we know that based on our Dirichlet boundary condition, for the last node, we already know the value of the solution. U of L is already G for the last node. And so for the last node, we don't need to solve this equation KD equal to F. And hence, we essentially apply the Dirichlet boundary condition to K and F by essentially removing the last row and column of K and removing the last row of F because we don't need to solve the equation for those particular rows. Now that we have assembled K and F, we essentially solve the linear system KD equal to F to get the solution D. So we begin by initializing the solution by zeros. And again, the solution has Nn is an Nn by 1 vector since we have Nn nodes and Nn solution values. Based on our Dirichlet boundary condition, the solution at the last node is already known is equal to G, whereas for the other nodes, the solution is determined by solving KD equal to F using this line over here. And now we're done in terms of the finite element method. We have the solution determined D. Since this is a pretty simple problem, it's possible to solve it analytically. So I've defined the analytical solution over here in terms of the domain L, domain length L, the Dirichlet boundary condition G, and the Neumann boundary condition constant H. And finally, we plot both the finite element solution as well as the analytical solution and compare them. And here's what we get. As you can see, both the FEM solution and the analytical solution agree pretty well, which tells us that the FEM method is working correctly. So one interesting demonstration that we can go through is see what happens as we change the number of elements in the mesh. So let's start by a very small number of elements, say 10, and run all the cells. And you can see that with 10 elements, the FEM solution is actually not matching that well with the analytical solution. The trend is correct, but the values, particularly at 0, are not matching. It's interesting that at x equal to 5, the end of the domain, it matches exactly. That's because we have the Dirichlet boundary condition there. So we are forcing the FEM solution to match with the true solution here. But as you move away from the Dirichlet boundary condition, you see that there's more and more deviation since we have very few number of elements. So now we increase the number of elements to 20, and then we run the cells again. And now you can see that it's much closer since we've refined the mesh. Let's continue refining. Let's move to 40 and then run all the cells again. And now we are even closer. And when we move to 80 and run all the cells again, then now we are like really close. And if we refine the mesh further to 160 and run all the cells, and then now it's almost overlapping with the analytical solution. So this simple demonstration shows that in the finite element method, as you refine the mesh, as you make the element size smaller and smaller, the FEM solution essentially converges to the analytical solution. So I think that's all I have in terms of this demonstration. I've included a link to this particular code below the description for this video. I recommend you to download it and play around with the code. You can try to change the forcing function, change the boundary conditions, and see what the solution looks like in that case. A few other interesting things, few exercises, if you want to familiarize yourself with FEM even more, is what would happen if we had, say, a Dirichlet boundary condition at both 0 or L and L. Or let's say we had a Dirichlet boundary condition at x equal to 0, but a Neumann boundary condition at x equal to L. How would this code change? So those are a few things that you can try if you want to get some more experience with this particular computer program. So yeah, I think that's all I have for this video lecture series. As we discussed, the goal was to solve the Poisson's equation in 1D, and we've done that. We've understood the concepts to do that. We have implemented the concepts into this computer program, and I hope you now have a better understanding of the finite element method in 1D. Thank you for listening to me, and I hope you learned something. Bye.